Great, thank you. Hello, my name is Christian Boersma, and I'm the project lead on the NASA Ames PA infrared spectroscopic database. It's great to have this opportunity to share with you our database and specifically the PyPAHdb tool that we have been developing for the PDRs for all JWST early release science program. First, I will go through some slides to give you some background. After this, my colleague, Alexandros Markodakis, will do a live demo of using PyPAHdb. So the slides are divided up into two parts. The first covers PA spectral databases. The second, the PyPAHdb tool we have been developing. So first, spectral databases. Shown here is the ISO SWS spectrum of the planetary nebula NGC 7027. Isolating and zooming in on the PA components reveals the richness of the astronomical spectrum with numerous discrete bands and features which are indicated by the blue dashed lines. Each of these bands can be attributed to a specific vibrational motion of an aromatic side group, which is illustrated using the PA coordinate here. The astronomical goal is to explain the richness of the astronomical PA spectrum and, by that, gain an understanding of the evolution of the astrophysical environment. This is where PA databases come into play, of which there are only a mere few. One is European, the other at NIST, and the last, the NASA Ames PA Infrared Spectroscopic Database, or PAHdb for short. Here we will focus on PAHdb. What makes PAHdb unique is that it not only holds the world's foremost collection of genuine PA spectra, but also provides necessary software tools and models to work with those spectra. In addition, all of this has been made available publicly through a comprehensive website. It is this trinity that allows users to readily analyze and interpret astronomical observations with PAHdb. The current version of PAHdb's library of computed spectra contains some 4,233 spectra, that of the laboratory spectra 84, and the recently added library of PA cluster spectra some 103. Each method of acquiring spectra, be it computational or directly from the lab, has its own advantages and disadvantages. This brings us to the ERS science enabling deliverable PyPAHdb. PyPAHdb characterizes emissions from PAS. It is a streamlined, accessible PAHdb Python tool. PyPAHdb decomposes astronomical PA emission spectra into contributing PA subclasses in terms of charge and size using a database fitting technique. The input for the fit are a pool of spectra constructed using the spectroscopic libraries of PAHdb and take into account the detailed photophysics of the PA excitation and emission process. One might ask, why database fitting? Well, spectroscopic assignments are based on computed spectra of actual aromatic molecules in specific charge states, structures, sizes, and so on. This allows the analysis of the spectra without the need of an ad hoc interpretation of the state of the PA population, since the average synthesized spectra can be traced back to the fully characterized individual PA molecules. The pool of astronomical PAs used in PyPAHdb meet the following criteria and include the fullerenes. That is, PAs not containing magnesium, oxygen, iron, silicium, no side groups, and not fully dehydrogenated, except of course for the fullerenes. To convert PAHdb's integrated absorption cross-sections into emission spectra, a PA emission model is used that computes the vibrational temperature after absorbing a 7 electron volt photon, following the entire emissions cascade, applying a redshift of 15 wave numbers to mimic some enharmonic effects, and using Gaussian line profiles with a fixed width of 15 wave numbers. PyPAHdb is open source and being developed on GitHub, which also hosts the documentation. Continuous integration is used to streamline development and ensures documentation stays mostly in sync with the code. The development of PyPAHdb has contributions from Matt Shannon, Alexandros Markodakis, who will give the live demo shortly, and myself. For more background details, though now perhaps a little bit outdated, PyPAHdb was presented at the 2018 Scientific Python Conference with proceedings available. Thank you. And now Alexandros Markodakis will take it from here with the live demo.
I will share my screen. Hello, my name is Alexandros Markodakis. I will be presenting the PyPAHdb demonstration. So as Christian mentioned, PyPAHdb is part of the science pack that was designed for the JWST Early Release Science Program PDRs for All. Here is a link here for a web version of the database where you can actually go and inspect molecules from the database perform some initial analysis, or even upload your spectrum and fit that all without needing to install anything. So this is kind of a limited, but still it gives you a good impression of the suite of tools. This is the link for the repository that contains all the suite of tools that are designed for PyPAHdb. And we will be looking at PyPAHdb, which is essentially a light version of the Python suite of tools that is designed. And by that, we mean that there is already a pre-computed matrix of Pi emission spectra that were taken from version 3 of the library. And Kristen just mentioned what are the criteria that were a certain pool of Pis were selected for PyPAHdb, and a specific emission model that was applied to get the emission spectra. So the general methodology consists of essentially loading in your spectrum, reading your spectrum, either a FITS file or an ASCII file, then loading the matrix of the pre-computed spectra, which are oversampled, and then they are able to be interpolated to the frequency grid of the observations. And then a non-negative least square fit is performed. And then we're able to obtain the breakdown into the ionization fraction, the large Pi fraction, and the charge breakdown, depending on the Pis that have been contributing to the fit. And by large Pis here, we mean Pis that contain more than 50 carbon atoms. And then in the end, we're able to write the output to disk, either both the FITS file from the breakdown and the a PDF for the plots. So here in this line, this is the line that we need to do if we need to install the package, but this is already installed here in the SDSCI, so there's no need to do that. This will also download a version of the database that contains the Pi molecules. And as Dri mentioned in his presentation, we will be using, for the example here, a JWST Galaxy Spectrum from an ERS program. And I wanted to mention that PyPAHdb is able to fit both single spectra as well as spectral cubes, and we'll be showcasing both. We will start from a single spectrum feed. So this is the spectrum for VV114, and PyPAHd was run, and we obtained the pure Pi component from PyPAHd, which we'll be using as an input in PyPAHdb. So the first things we want to do is to import a few models that will help us plot and read our input data, as well as import the two main classes of PyPAHdb, the observation class, which handle the observations, and the decomposer class that does the decomposition and the fitting. So we will run this. And then we just need to point out where our data is. In this case, the JWST spectrum is included with the installation of PyPAHdb. So we're just using the package resource module to point where the installation directory of PyPAHdb is to locate the template. And then we only need to construct an observation object by using the observation class and the input spectrum, and then just fit this observation object using the decomposer and in the observation object in the spectrum property. So I will just run that. And then we will be able to simply plot the results in the fit objects just by doing fit.plotFit. And this will create a multi-panel figure. So on the top, we have with black our input spectrum, with red is the fit. Right below is a residual spectrum, and then we get the breakdown in large and small Pis that have been contributed in the fit. We get the large fraction here, and we also get the ionization fraction and the charge breakdown to anions, neutrals, and cations, again from the individual molecules that were used in the fit. We are also able to access those derived fractions just by printing from the feed object, just printing feed.ionized fraction and feed.large fraction, and this will give the same essentially values that were printed also in the PDF. And now we will move on to feeding a spectral cube. For this example, we will be using a Spitzer cube, the reflection nebula NGC 7023, the Iris Nebula. And again, the philosophy is exactly the same. So we will simply need to point out where our spectrum is, and then we will construct an observation object with the observation class, and then we will feed that object with a decomposer. And for cubes, also, we have the option to enable multiprocessing, so that will speed up things. And then we will just continue to plot the results. This is here a helper function just to lower the dimensionality from 3 to 2 in the cube and get rid of any header cards associated with the third axis. And then just in the fitted objects, I will just do plot map, and then I will use whatever property I want to plot. In this case, I want to plot the ionization fraction map. And here I will just give the label for the color map and the WCS from the cube if I want to do that. And running that, it will give us the ionization fraction map for the spectral cube from the decomposition. And I'm also able to access the individual pixels and get the fit and the breakdown from that. And to do that, I just go again to the feed object and write plot fit and then the pixel coordinates of interest. So by doing that, it will create a similar multi-panel figure, just like in the one single spectrum case, where we have our fit, the residuals, and then the breakdown to large, smalls, and charge breakdown. Here's just an example of how we can access and inspect some properties. For example, the shape of the cube and the maps, and some helpful keywords that are available. Just again, going to the feed object and going through the different keys. And then, of course, we are able to save both our plots and the results file into a feeds file. The command is going to be, again, in the feed object, just save PDF and save feeds. And this, by running this, should create 2 files that are were already here for me. The feeds file with the feeds and the breakdown, and the PDF file with the plots. And we have the option to load back the feeds file and inspect again any of the results, or even do plotting. So we're just going to we're going to open the feeds file here, and here we're printing all the header keywords. And for the plotting, we just need to call the decomposer class that has the plot map method. And then we're loading our data slice. And for this example, now we're going to just plot the large fraction key. And this is going to show the map for the large fraction breakdown. So this is essentially as simple as that. Is the tools and the commands that someone needs to use to feed a spectrum with PyPAHdb. Now, if you want more flexibility, more options, for example, if you want to apply a different emission model, if you want to use a different pool of molecules, or have access to latest databases, then you will need to use the Python suite of tools, and I will briefly tease that here. So again, this is already installed in the system. We don't need to run that. One of the main differences here that the Python suite of tools does not come with a library of PA molecules included. This has to be downloaded separately. It's a kind of large file, but with the installation, a cut down version of the library is included. And so the first thing that we need to do is point where our library is. So this this line here will be looking into the cut-down version of the libraries. And then we're just going to import the main module of the Python suite, which is the PyPAHdb, which is going to parse the database and give access to the different properties there. So here I'm just going to create, I'm going to parse and instantiate the database, and I will create a PyPAHdb object. So again, I'm just going to be pointing where the installation of the Python suite is to go and read the XML version of the database. So if you want to actually download a complete library, this is the link to get the complete library versions. And for the example here, we're just going to be using one molecule. So each molecule is assigned a unique identifier, a UID. Here we have the option to input as many molecules we would like. So we have to create a list and give as many molecules we wish, or even set up search criteria where we're going to search the database. So for this case, we're just going to be using Carnine, which we know the UID is 18, and we will use the method the get species by UIDs in the database object, and I'm going to run this. It's going to parse the database first, and then it's going to assign Carnine all the data from the database. And now we're able to, we have the option to inspect the chemical structure, and then we just need to call the geometry module to do that. And all the modules have a plotting function in them. And so the first step is to call essentially the module and then plot the, call the plot function to view the structure of the molecule. So in this case, it will give us the plot for Carnine. And then we're able to get the transitions for Carnine. And then for that, we just need to call the transitions method, and we can plot that and get the stick spectrum for that. And once I do that, you will see the spectrum, the stick spectrum here. We're able to make an absorption spectrum as well. For that, we need to convolve. And now we have more flexibility with PyPAHdb. This would be a Gaussian with a specific pool. We have maximum here. We have the option to do Lorentzians, Broods, and set our own full width have maximum. For this example here, it's going to be a Lorentzian. And this will convolve the stick spectrum and give us the absorption spectrum here. And we can also set up an emission spectrum. Again, we have the flexibility to choose different photon energies. For this example here, we will be using an ADV photon energy. The full cascade is going to be taken into account to calculate the emission bounds, and these will be convolved again. For this example, we're just using Drude profile and a specific full width of maximum, and we're going to plot the emission spectrum. Here's the result. I will stop here, and I will just say that you can build you can select your PAH molecules from the complete database. You can set up your emission model, and then you can use all that to fit your input spectrum. Thank you.